In this example, we'd like to show that a geometric series, which is a sum of a geometric sequence, converges if and only if the magnitude of the r, the common ratio, is less than 1. So the first thing we need to talk about is an infinite series. When does an infinite series converge? So let's suppose that this series is convergent. So n equals 0 to infinity, a0, a sub 0, r to the n. If it's convergent, then it's going to add up to some sum we'll call s. And this sum s, there has to be a systematic way to actually compute this sum, right? So how are we going to compute it? Well, what we can do is we can make a sequence of the partial sums. So a partial sum of any series, but this one in particular, a partial sum of this series. So again, this is an infinite series. It just goes on and on and on. The partial sum here is going to be, we'll denote it by s sub k, and it's going to be the sum from n starting at 0 up to k. So it's going to be the sum of the first, in this case, k plus 1 terms because it starts at 0. And for us, it's going to be a sub 0 r to the n here. And so when we add this up, what does the partial sum s sub k look like? Well, it looks like the first term, a sub 0 r to the 0, plus, and then every successive term multiplies the previous term by r. It's very similar to the geometric sequence that we studied in the last lecture, except now we're adding up the terms. So the next one is going to be a0r plus a sub 0 r squared, and this goes all the way up to a0 r to the k. All right, so now the question was, though, how are we going to be able to compute this sum, or how are we going to be able to say that this sum legitimately exists? And you know, this course is not a calculus course, but Calc 1 is a prereq, so we know what it means to be a limit. And what we can say here is that no matter what, when you take a partial sum, this is a sum of finitely many numbers. So this one is always going to be convergent, right? Because it's a finite sum. This is always going to add up to some number. So every partial sum, even if your k is very, very, very large, this will still be a number itself. And so we can make a sequence of the partial sums. So the sequence of partial sums, we can just call this s sub k, because that's what they are, right? But this is going to look like partial sum s sub 0, s1, S2, S3, etc., right? Up to this formula for Sk, but then beyond as well. Because we can plug in any integer for k, and we can then, at that point, we can think about what happens to this sequence if we try to take a limit as k approaches infinity. So what's happening to the sequence, to the terms of the sequence? Is anything happening? I don't know, it's not so clear. So if you've taken Calc 2, then you've already studied this. If you haven't taken Calc 2, then you'll see this again. And really, we are not going to do too much with this, so you don't need to worry about the fact that this is in Calc 2 and not Calc 1. Because for us, what we're going to do is we're just going to try to find a formula. So this is our plan of attack here. Our plan is to find a formula for s sub k. That's the sequence now. We're going to treat it as a sequence of partial sums. Find a formula for s sub k, which again, we can write it as in function notation if we want. And since we're going to take a limit, that seems like a nice thing to do, right? So find a formula for the partial sum s sub k, and then, if possible, we're going to take the limit as k approaches infinity of this s sub k. And if that exists, if that equals a number, then that number will be the sum of our infinite series. All right, that's what it has to be. So let's do it. Now we've already written out a formula for the partial sum itself. So recall here, we just did it, so it's not hard to recall. But s sub k, I want this to be written down here. So we have s sub k equals a naught plus a naught times r plus all the way up to a naught r to the k. What I'd like to do now is take another copy of this same partial sum with the same value of k, but I want to multiply the whole thing by another copy of r. All right, r is the common ratio. I want to multiply by another copy of r. Well, what's that going to do? It's going to take this whole sum, but it's going to multiply each of these by an r. So the first term in this one is going to be a naught times r. The second term is going to be a naught r squared, right? And then these are going to add up, and then the next one here is going to be a naught r to the k. But there's going to be one more, right? There's going to be one where this a naught r to the k was actually multiplied by another r. And so we can line these up like this. And at this point, I want to subtract these two. So subtract these two term by term. On the left-hand side, look what we have. All right, on the left-hand side we have s sub k. So we have s sub k minus r times s sub k. On the right-hand side, when we look at this, we see we have a naught. So a naught is there. And then we have a bunch of stuff that's going to cancel. We're subtracting away the bottom from the top. And so at this point, the only other term that's left on the bottom is minus a naught r to the power k plus 1. Okay? A sub 0 here is a finite number. That's the first term in our sequence, which then we turned into a series, but it's the first term in the sequence. And s sub k is itself also a number, as we just discussed. So we can factor this a little bit more. And on the left-hand side, we have 1 minus r s sub k. On the right-hand side, we have a naught times 1 minus r to the power k plus 1. And then solving for s sub k, that's our goal, we get a closed formula for the partial sum. It's our first term, a sub naught, times 1 minus r to the k plus first power, all divided by 1 minus r. All right? And so we immediately see that we have a restriction on r, right? R cannot equal 1 here. So r cannot equal 1, or else our partial sum won't even make sense, right? So r can't be 1. So we've got that. There's a restriction. By the way, remember what we're trying to show. We're trying to show that after all this work that the magnitude of r has to be less than 1. So we've got 1 off the books here. Our next job is to try to take the limit, right? So we're going to take the limit. So we take the limit as k approaches infinity of s sub k. Well, that's going to be the limit as k approaches infinity of this term, which has, at least with respect to k, has a whole bunch of constants. There's a k right there, right? A naught 1 minus r to the power k minus 1 over 1 minus r. But 1 minus r is a constant. A naught is a constant. This k is the only one where the limit's going to hit, right? So this then becomes a naught. And this can go in by continuity, if you want to go back and review some Calc 1 terms. But by continuity, actually, it can go right upstairs here, right? Limit k approaches infinity, k plus 1. I don't know if it needed to go way up there. Yeah, let's take it down, actually. So we'll write it like this. And then we can ask, what does this limit look like, right? So from this entire thing, this portion right here is the only portion that we have to consider now for this limit. So we'll just state some facts from calculus. If you need to go back and review these, this is fine. But if indeed the absolute value of r is less than 1, then as you raise that value, that number, r, again, whose magnitude is less than 1, to bigger and bigger powers, that number is going to get smaller and smaller, right? So in this case, the limit as k approaches infinity of r to the k plus 1 is going to equal 0. It's going to go to 0. Okay? On the other hand, if the absolute value of r is greater than 1, then what's going to happen? Well, two things could happen. If it's completely positive, so I'll even write it this way, because this is what really matters, the absolute value of the power. So r could be negative, right? And if r is negative, it's going to keep swapping signs. But even if it's swapping signs, the thing that really matters is that the magnitude of this thing is going to blow up, right? This is a number bigger than 1, and you just keep multiplying it by itself over and over and over and over again. And so this will be infinity. And if this happened to be a negative number, it just oscillates back and forth between positive and negative infinity. And so either way, that's a limit that does not exist. And if the limit does not exist, then the sequence does not, that number s, the sum that we're looking for, does not exist at that point. There's only one more case because we ruled out 1 itself right here. The only other one to check is what about r equals negative 1? But before we do so, let's actually write down what happens. What happens if the limit does converge to 0, right? Well, if that's 0, then this is gone, right? So here's what we know right now. So if the absolute value of r is less than 1, then this sum, n from 0 to infinity, a naught r to the n, this thing converges, and it converges to a sub 0 times 1 minus 0, so that's just a sub 0, over 1 minus r. All right, and actually that's a really beautiful formula that I hope you guys have all seen before, and if not, you've seen it now, so there you go. The only outline question, so by the way, if r is bigger than 1 or if it's equal to 1, then this thing does not converge, right? This series does not converge, does not add up to a finite number. The only remaining question is what if r is equal to -1? Okay, so if r is equal to -1, this is the only outlying question now, then our series, we just go back to our series itself. So forget about the whole argument we had to do with the partial sum, but the sum then looks like a sub 0 times -1 to the n. And if we write out the terms of this, this is going to look like a sub 0 minus a sub 0 plus a sub 0 minus a sub 0 plus a sub 0, etc., right? And just look at this. If we think about the partial sums again, what's going to happen? The partial sums that are 0, 2, 4, etc., so the partial sums s sub 2k, these are going to add up to, there's always going to be a leftover a sub naught. A naught, right? And so that partial sum is going to be a naught. Well, what about the partial sums that have an odd index? So if we have an odd index, then look at these two combined, they're gone, right? These two combined, they're gone. The next one here combined, they're gone. And when this is s2k plus 1, then this partial sum is equal to 0. And as long as your a naught is not 0, which by the way, if a naught's 0, then all of this argument was kind of pointless because everything is 0 at that point, right? So if a naught's not 0, then there's no way that this sequence of partial sums can converge, right? There's no way. And so in this case, our series itself is also divergent. So divergent just means that it does not converge, does not add up to a finite number. But this right here is what I want you to take away from this. The argument is a good one, so make sure you understand the argument, but that result is something that you should just know from now on. We don't have to prove it again. We've proved it once, so we're all smiles. Let's leave it there.